Okay, so the camera died, so I'm going to jump in on 31. So it says that these two masses hang freely. This sits on a frictionless table, so don't worry about friction. M3 accelerates down, and M2 accelerates to the right, and M1 accelerates up, so the system is moving around like clockwise. And right now, it accelerates with the acceleration A. Now, if the mass m, so this mass right here were increased, what would happen to the new acceleration? Would it be more or less or the same as before? So let's think about m3 is the force that is like your net force, kind of, subtracting this force pulling back. This is the force that is causing it to move in this direction. So if you increase this mass, now you have a greater force pulling down, which is like pulling the whole system around like this. So you should have more acceleration than before. Now if mass 2 were increased, so if I increase this mass, so this mass does nothing except for take up like mass, the total part of the total mass right here. It doesn't help pull to the right or pull against it. It's just increasing the total mass of the system with the same net force as before. So more mass to pull means less acceleration overall. And then finally, if the M1 were increased, what would the new acceleration be? So if I increase this mass, first of all, there's more total mass. And if I increase this mass, you have more force pulling against the system. Like you literally have a greater weight pulling down, which is against the acceleration of the system. So it's less mass because you have an extra force against the motion, and you have more total mass to spread that over. 34. So this is very, very similar to number 22. Yeah, number 22 that we looked at earlier. I have two objects sitting on top of each other. This one is connected by a rope to the wall, and then this one is being pulled right here to the right. And it says the coefficient of friction between the blocks is 0.7, and we are looking for the coefficient of friction between the 10 kilogram and the floor. So it helps to draw a free body diagram. So the 10 kilogram obviously feels its own weight of 100 newtons, and it feels this force of the 5 kilogram box on it. So I'm going to say this feels a force from the box, and the box exerts a 50 newton force down. It's just the weight of the box really acting on this guy. And then the only other force is the normal force, and because it is balanced up and down, then the normal force would be equal to 250. Now it feels some applied force of 45 newtons to the right, and I have the force of friction between the box and the floor, so that would be the force of friction from the floor, and then the force of friction on the box from the other box. So both of these would be opposing its motion, like pulling back on both of these. This is also a friction force, but now it's the friction from the box, not the friction from the floor, like before. We have the coefficient of friction between the blocks. So I think it's a little bit easier to think about this 5 kilogram to find the force of friction. So it has its own weight of 50 newtons, and then it feels a normal force from the block, not from the floor. So I'm going to call this F normal from the box, and the force of the box on one another is 50 newtons. That means this box is pushing up 50 newtons. And also that makes sense because it's balanced up and down. And then there's a tension pulling this way. And then whenever this one tries to slide away, so when you pull this way, this one is pulling the friction back. And then this, it's really hard to explain while I'm pointing up here. Basically the friction of the 10 kilogram on the 5 kilogram would be to the right, like this. And then we want to find this force of friction. So force of friction is mu Fn. I'm finding the friction between the boxes, so I want to use the coefficient between the boxes, or blocks, whatever you call it. So I'm going to use 0.7. And then the normal force is the normal force between the boxes, which is just 50 newtons. So that's going to give me 35 newtons, which is what this one has to be, because the force of friction from the box is the same between the boxes on the first box or the second. It's the same friction force. Now the friction force between the floor and the box is going to be different. The friction force between the floor and the box will be the mu, the coefficient between the box and the floor, and Fn. And that normal force is the normal force that the floor is exerting on the box, which would be the 150. So mu 150. And then it's saying I need to know the force of friction, but it says that the block needs exactly 45 newtons to start moving. So if there's 35 newtons of friction from the box and you need exactly 45 newtons to get it started moving, then the force of friction on the floor must be 10. So then you just plug in the 10, divide this over, and you get a super small number, 0.067. And that would be your answer from you. Okay, cool. Study hard. Good luck.